So now we're ready to move on to the cosine function. We're going to define the inverse cosine function. And to get started, we're going to look at a graph of cosine. So we're starting with the cosine wave here, different from sine, right? Because we start at 1 when x is 0, and then we go down to 0 at pi over 2, negative 1 at pi, 0 at 3 pi over 2, 1 at 2 pi. That's the pattern of the cosine. And again, we do not have a function that is one-to-one, so the full cosine wave does not have an inverse. But just like we did with sine, we can restrict the domain of cosine to an interval of x values over which the function is one-to-one. And that's what we're going to do right now. And we certainly would like to use, it would make sense to me, if we could use exactly the same interval that we used for sine. Now, starting out too, I think the thinking is we want to keep the y-intercept value at the point at 0, 1 if we possibly can. And now, if we start from that point at 0, 1 though, immediately we run into trouble if we try to extend in both directions from that point. Because up on the graph of cosine, if you go both to the left and the right of 1, we start coming down on each side from this max point, and that's going to mean we don't have a one-to-one function. So there's no way to move toward negative pi over 2 and pi over 2 and obtain a restricted domain over which the function is one-to-one. So what we do is we just go in one direction. We start moving to the right, and actually I'll think of it up here. We keep the point at 0, 1, and we just move to the right. We can't move to the left. We lose one-to-oneness. We move to the right, and we keep going as far as we can and still maintain a one-to-one function. So for this red portion, we hit the x-axis at pi over 2, we can keep going. Because even if we dip below the x-axis, we still have a portion of the graph that's one-to-one. There's a horizontal line will not cross the red graph more than once. And we can come all the way down to pi, the point at pi, and once we get to here, if I go any further, then I start rising from a midpoint, and I can't continue because we would lose our one-to-one property if I tried to take a larger interval beyond pi. So what we end up with is this piece of the cosine graph. Unfortunately, sadly, we have not chosen the same interval that we got to choose for sine. We restrict the domain of f of x equals cosine x to the interval from, well, we're starting at x equals 0, we go out to x equals pi, 0 to pi. Same as the red portion that I marked up above. The range is still from negative 1 to 1. So we chose an interval of x values that give us points that use every possible y value between negative 1 and 1, including the endpoints on the graph. So now we have a one-to-one function so we can define f inverse, the inverse function, just like we did with sine. I think it's probably worth asking or talking a little bit about, well, if we got to use this interval 0 to pi for cosine, maybe we could go back to sine and use that interval for sine. Here's my sine wave. But notice 0 to pi won't work for sine because sine is not 1-to-1 on that interval. It really just turns out there's no way, unfortunately, to choose the same interval. And this is a complication that we're going to have to deal with. The interval that we chose for sine is different from the interval that we're now choosing for cosine. Okay, so let's now try to, what we want to do is actually graph our inverse function. I have another copy of the restricted graph of cosine here, and I think I just want to point out that this point is pi comma -1. This point right here, if I label both coordinates, that's pi over 2 comma 0. The y-coordinate is 0. And then this y-intercept point is 0 comma 1, right? X is 0, y is 1. Those are 3 points that we have in our graph. And what I want to draw is what we're going to call f inverse of x is cosine inverse of x. So we use that -1 notation, just like we did with sine. This is the cosine inverse of x. And so now let me set up my x's. Actually, I want to draw that down lower, so I'm just gonna come down lower. I'm gonna ignore that one line that I just drew. And my vertical axis points at 1 and -1. I'm now going to label on the horizontal axis. And 0, pi over 2 pi, I'm going to put on my vertical axis. And let's see, to draw my graph, instead of the point 0, 1, on the inverse function, I'm going to have the point 1, 0. 1, 0 is right here. 1, 0. Instead of pi over 2, 0, I'll have 0, pi over 2. And instead of pi -1, I'll have -1 pi just pi and I gotta figure out the wiggle we're going to have again. I could have taken the cosine graph, flipped it over. I don't have a copy of that here with me. I'm just going to show you what this guy turns out to be. Is something like so. There's our graph of the inverse cosine function. So I put the name way up there. There's the graph. And now, what's the domain in range of this function? The domain of the inverse is the same as the range of the function we worked from. So the domain of the inverse is -1 to 1 with square brackets. The range of the inverse is the same as the restricted domain of the original function. So that's the interval from 0 to pi. And cosine inverse of x is also written as ARCCOS, x, arc cosine x. And we won't use that notation, but you will see that in other textbooks, maybe in Desmos. And keep in mind, I guess I'll write this down again too, cosine inverse of x does not mean 1 over cosine x. The inverse function is not the same thing as reciprocal or 1 over, and we gotta always keep that in mind. Cosine inverse of A equals B means, so this is like saying input A, output B, or the point AB on the graph of the inverse cosine means the point BA is on the graph of cosine. So it means cosine of B is equal to A. And we got to keep in mind our domain restriction, and the domain restriction we made to cosine that ended up being the range of our inverse function. 0 is less than or equal to B is less than or equal to pi when we're working with the inverse cosine. Okay, so there's inverse cosine graph, which you got to know and be able to draw. And the way I draw it is I actually remember the restricted graph of cosine, and then I just interchange coordinates and axes to get my inverse graph whenever I need it. Okay, so now I think we're ready to do, we're going to do a few problems right in this video. And up at the top of my sheet here, I have, just as a reminder, our relationship between cosine and inverse cosine, our defining relationship. And so let's go right into some exercises. All right, number 1, I'm going to find A, cosine inverse 0, and B, cosine inverse negative square root of 3 over 2. Let's do A first of all. Cosine inverse of 0. Now, just like with sine, the quantity inside the regular cosine, or what corresponds to what's outside the regular sine, is an angle, or cosine inverse of a number equals an angle is a way to think of that. So this cosine inverse is 0. I can think about it by I can work on it by letting theta equal cosine inverse of 0. Then I can rewrite this as cosine theta is equal to 0, and theta has to be in that restricted interval from 0 to pi. So and the question is, what is theta? Okay, I guess in this case, I could just go back to my graph, and I would like to go back to the cosine graph. Oh, here it is. Just want to, I get more help out of thinking about the cosine wave that I know really well and thinking about the restriction that we took between 0 and pi when I'm figuring out some of these problems. Sometimes this is more helpful for me than using the inverse cosine graph, because we're saying cosine of an angle is 0. Well, when cosine is 0, on the cosine graph, we're right on the x-axis, right? That's where the cosine values are 0. And we have to be within this interval from 0 to pi. Well, the one spot where this graph crosses the x-axis is at pi over 2, so theta equals pi over 2. So cosine inverse of 0 is pi over 2. There are other angles whose cosine is 0, but this is the only angle in that interval from 0 to pi that has this cosine. B cosine inverse of negative square root of 3 over 2. Looks like we're going to be working with some of our favorite angles here. And again, I can let theta equal cosine inverse negative square root of 3 over 2. I mean, this reminds me that we're looking for an angle. You know, we want to find out what theta is. That's what the answer is here. But if I rewrite this as cosine theta equals negative square root of 3 over 2, it's a little bit easier for me to think about it. And my interval of restriction here is 0 to pi. Let's think about the unit circle. So cosine of what is positive square root of 3 over 2? That's pi over 6, right? Or 30 degrees. So if I just think about my 30 degrees or pi over 6 angle on the unit circle, cosine is square root of 3 over 2, the x-coordinate. Sine is 1/2. Now, I want my cosine to be negative square root of 3 over 2, so I need an angle whose terminal side is where x is negative, if I'm working from the unit circle. And now this 0 to pi interval on the unit circle makes me think of the upper half of the unit circle, right? From 0 to pi radians is like 0 to 180 degrees. So this restriction from when I think of the unit circle is telling me I'm looking at the upper half of the unit circle. I need a negative cosine. I need to be over here where the x-coordinate is negative. The y will still be 1/2. And this is the angle I'm looking for because that's the appropriate angle between 0 and pi. It's got reference angle pi over 6. So I know this is going to be pi minus pi over 6 or 5 pi over 6. And you can also just read that off of your unit circle diagram. So theta is equal to 5 pi over 6. And that means that cosine inverse of negative square root of 3 over 2 is 5 pi over 6. Okay, a few more problems. And I think I'm going to, oh, I guess I should leave that up there for a couple seconds. And then what I'm going to do is I'm going to bring that back into the picture and we'll start a new sheet. Exercise. We want to find following: A, cosine of cosine inverse of 1/4. B, cosine inverse of cosine of pi over 12. And C, cosine inverse of cosine of 3 pi over 2. All right, so let's start with A, cosine of cosine inverse of 1/4. Now, here is a situation that's kind of similar to something we saw with sine, where I'm going to call something theta in this, but it's not the whole expression, it's the output of the inverse function, because the output of the inverse function is an angle. So I'm going to let theta equal cosine inverse of a fourth, so that cosine theta is 1/4, and 0 is less than or equal to theta is less than or equal to pi. Now what do we want? We want cosine of cosine inverse 1/4, which is cosine of theta. But cosine of theta is 1/4. It's staring at us right in the face. We're done. That's it. And in fact, when you apply a function and its inverse, you would normally expect them to cancel out and take you right back to where you started from. And that's exactly what's going on here. Let's look at B. B is cosine inverse of cosine of pi over 12. Now, what we don't want to do here is, I don't want to do this. Call this theta. That doesn't make sense, because this is the regular cosine function, and the output of the regular cosine function is not the angle. The angle's on the inside. We already have an angle in here. So what I can do, though, is I can let this entire quantity be theta, because on the outside I have the inverse cosine. The output of that will be an angle. So it does make sense here to say let theta be the entire thing. Cosine inverse of cosine pi over 12. And then I can rewrite it as cosine theta equals, now I still have cosine pi over 12, and 0 is less than or equal to theta is less than or equal to pi. Well, cosine theta equals cosine pi over 12. I think we can see theta has to equal pi over 12. And my blue ink is running out here, so I'm going to write in red. So cosine inverse of cosine pi over 12, the original problem, is just pi over 12. That's our answer. And this is another case where when you apply a function and its inverse in a composition, they tend to cancel out and leave you right back where you started from. That's not always the case, though. So there's this exception, and so we're going to look at C here. One more problem. Cosine inverse of cosine 3 pi over 2. It looks just like B, right? But it's not. So there's a little fine point here. Usually, I mean, in most normal situations, a function and the inverse, when they're composed, cancel out and leave you with the value you start out with. Same here. The situation in C is a little bit different, though. I am going to call the whole thing theta. So I'm going to let theta equal cosine inverse of cosine 3 pi over 2. Then I can rewrite this as cosine theta equals cosine of 3 pi over 2. So it's this inverse cosine that goes away and becomes the cosine here. The other cosine stays. Now, again, it looks just like what we did in the previous problem. Theta is 3 pi over 2. But now I'm going to just draw my portion of the cosine graph that we restricted to define the inverse cosine function. So this is that interval from 0 to pi. This is a restricted y equals cosine x. Okay. 3 pi over 2 is way the heck over there, right? Cosine of 3 pi over 2, we know that's 0, right? Cosine of 3 pi over 2 is 0. But the theta we want here is an angle whose cosine is 0, but lies within the restricted domain. So 0 less than or equal to theta less than or equal to pi. This condition has to be met by our answer. So theta equals pi over 2. Pi over 2 is where the cosine is 0. It's a point on the x-axis. It's true, cosine of 3 pi over 2 is also 0, but it's not in the restriction area for the cosine function. So theta equals pi over 2 is what we want, and we can say cosine inverse of cosine of 3 pi over 2 is equal to pi over 2. So this one you got to think about quite a bit, because that should seem strange that we're composing an inverse with a function and we're not getting back the same thing. And it's because this 3 pi over 2 is outside the interval of the restricted domain, and so that kind of cancellation property no longer applies. That's our last cosine problem. Next up is the inverse tangent.